The last thing that I want to touch on here is how to calculate the amount of energy that is required to deform a system. And this comes back to some of the basic things you probably learned in your intro physics class. The work, so force as a function of time, results in some deformation u as a function of time, and u is often used for straight deformation, whereas we use epsilon for strain. This might have an area A, and you can also think about this as the length L and the total length L of t. But if it's elongating at a rate du dt, or u dot, this creates strain in that material. The power is energy as a function per unit time. It's a function of time required to cause the deformation, and that's the force that we apply times that rate of elongation, because we know this is all happening through time. But because we want to use the relative sense of these, we can take F u dot, and we know that F has to be divided by A to turn it into a stress. U dot needs to be divided by the length in order to turn it into a strain rate, because remember, strain is the change in length over that original length. And if we look at this, we end up getting the stress times the strain rate. So this is power as a power as a per unit volume is this. Note that we are just multiplying stress times the strain rate. So if the strain rate is not going anywhere, if the strain is steady, then this becomes zero. It's the rate of change of strain that results in power. So we can be applying a stress, but if there's no strain, if the strain is not changing through time, then there's no power associated with that. The total energy then is the integral of the power. So energy as a function of time, starting from 0, so you could say it's the change in energy from time 0 to time t, is the integral of our power as a function of power per unit volume. So if we do 0 to t, we're integrating the stress through time and the strain rate through time, dt prime. So if we do this integral for elastic and viscous behavior, you can see that there is no change, that for elastic behavior, where the stress is equal to mu times the strain, if you plug in that stress into that equation, you end up getting that the change in energy is equal to mu times epsilon dot dt prime, which gives you 1/2 mu epsilon squared of t which is also equal to sigma squared over 2 mu. So what this is saying, that while it's stretched, you did apply a certain amount of energy, but you get that energy back when the stress goes back off to 0. So the energy, you get the energy back that you put into it. So energy is recoverable. This is a key point of elastic material. If you do the exact same thing for the elastic component, with the change in energy, for the viscous component, you plug in what we know our viscous is in terms of the stress times the strain rate. This actually has a value, if we integrate it through time, if there's any kind of deformation happening, then this will always be a positive energy in the end. So the squared means that whether we are going faster or slower, if we do the strain rate in a positive direction and then in a negative direction because we square it, so this is non-recoverable energy. So you always lose energy with the viscous process. And in the notes, I go over the process of harmonic loading, and you can actually figure out the energy loss because of the viscous part of harmonic loading, even if mostly that harmonic loading is elastic. So this is where you end up getting the attenuation of seismic energy, for example, in a system, because there is some loss of energy due to the viscous nature. The viscous nature is very subtle for a seismic wave traveling through rock, but there is some non-recoverable energy.